And welcome, ladies and gentlemen, to our next installment of calculus lesson videos. Just a brief note, I've been told in the past that this cartoon is funny, but I also have been told that you have to watch the movie, or not the movie, but the TV show House to understand it. So if you are a fan of House on TV, perhaps you like this comic strip. If not, we move on. Today, ladies and gentlemen, we look at L'Hopital's rule. Now, as I mentioned in class yesterday or today, whenever you're watching this video, L'Hopital's rule is a shortcut means for taking complicated limits. Now, we have in the past mentioned indeterminate forms, 0 over 0, infinity over infinity, and so on, things that do not exist in nature. For instance, if you consider 0 to the 0 power, it's a conflict of two rules. We've always been told that 0 to any power is 0, but anything to 0 power is 1. So how can we put the two together and reconcile? And the answer is we can't. They don't exist. So when we run into these situations in limits, we always had to do some kind of simplification, whether it was factoring, rationalizing, yada, 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 yada. L'Hopital's rule allows us to get around that. It's actually much faster, much faster. Mr. Rowland just came in and left. Always the interruption, Mr. Rowland. The first indeterminate form is that of 0, 0. If functions f and g are both 0 at a, then the limit as x approaches a cannot be found by using just regular limits. And we must do L'Hopital's rule. Now, the big question is, what is L'Hopital's rule? If you are taking the limit of something that does turn out to be 0, 0, as is defined here, then we are allowed to do this right here. We are allowed to take the limit of the derivative of the top over the derivative of the bottom. And this, ladies and gentlemen, I cannot tell you how much time in the end this saves. You're going to be amazed at how simple some of these problems become. So we start with this one. Now, just so you know, in the past, when we worked this problem, we would have to have rationalized it. I would have had to have multiplied by 1 plus x plus 1 over 1 plus x plus 1. Do the FOIL method, do all kinds of simplification. It would have taken a very long time to work this problem. But there's an easier way. I recognize this as an indeterminate form, 0 over 0. If I plug 0 in for x, radical 1 is 1, 1 minus 1 is 0 on the top, plug in 0 on the bottom, you see what you got. So I'm going to take the derivative. Now, radical 1 plus x, remember, is to the 1/2 power, so I can take the 1/2 out front, subtract 1 on the exponent, and that's how I get this. The derivative of negative 1 is nothing, and then on the bottom, the derivative of x is 1. Now, if I were to plug in 0, or simplify first, now if I plug in 0 for x, you see that it no longer gives me an indeterminate form. I have 1 to the 1/2, which is 1 times 2, and that gives me an answer of 1/2. Now, just those 4 steps alone was less work just in rationalizing this function right here, which then we would still have more work to do afterwards to plug in the number and simplify. Sorry about that, ladies and gentlemen. I had another interruption, and by the time I figured out where I was, I think I've messed up the video, so hopefully this won't be too confusing to you. I hope we've not already started this one on the video. If so, again, I apologize. Our next job is to calculate this one. And again, I recognize this one as being L'Hopital's rule. If you plug in, you get 0 over 0. So I take the derivative. So the derivative of radical 1 plus x, what it was just a moment ago. The derivative of x over 2 is 1/2, and then we have 2x here. Now, I could leave this the way it is, or I could try and simplify it just a little bit before I move on. So to get rid of these 1/2s, I'll multiply everything top and bottom by 2, and it gives me this. Now, I could do some more simplifying. I could try and go ahead and do the derivative. Let's go ahead and do the next derivative, because the reason I have to do the next derivative is if I were to plug this in right now, I get 0 on top, because this is 1, minus 1 is 0, and I have 0 on the bottom again. That being the case, I'll do L'Hopital's rule again. So I'll move my 1/2 out front, and I'll subtract 1 again. The 1 goes away, the 4x becomes 4. Now if I were to plug in my 0, I have 1 plus 0, that's 1 to the negative 3 halves, which is 1. So I end up with negative 1/2 over 4, which does give me negative 1/8 as an answer. And now for our next problem. Ladies and gentlemen, if you get anything out of this video at all, I'll be amazed. My computer is doing all kinds of crazy things, for which I apologize. Our next problem is a one-sided limit. Pictures are showing up, not showing up, things are going out of order, it's ridiculous. Anyway, one-sided limit. Remember, one-sided limits are the ones that have the little pluses or the minus. In this case, we're taking the limit as x approaches 0 from the right. Now, I've got the graph here. This is the graph of sine x over x squared. And as I approach 0 from the right, you see as I approach 0 from the right, it does climb up, 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 up. Now, we can verify this using L'Hopital's rule. If I were to apply L'Hopital's rule, and I can because right now it's 0 over 0, I have this, cosine over 2x. Now, how does that give me an answer of infinity? Because we've just shown that this function does go up. Well, cosine of 0 is 1, 2 times 0 is 0, and remember, anything over 0 is plus or minus infinity, and we would tell which one it is by looking at the graph. In this case, it is plus. Alright. Then we have the limit as x approaches 0 from the left of sine x squared. This time we're coming from the left, and we see from this one it should be negative infinity. Notice that we have the same function. The derivative of sine is cosine x squared is 2x. And so again, we would have 1 over 0, which is infinity, and we go to the graph to look and see if it's plus or minus. So the whole point of this was just to remind you that if you are going to get infinite answers, plus or minus infinity, make sure you go to the graph to look, see if it's plus or minus. Alright, our next problem. We have a problem this time of the form infinity over infinity. Ladies and gentlemen, this is the second of the most common indeterminate forms, the first being 0 over 0. We're going to calculate this limit. Limit is x approaches pi over 2 of secant over 1 plus tangent. You will find sometimes in these problems it's best to apply L'Hopital's rule right away, and sometimes it's best to simplify. In this case, I know that secant is 1 over cosine. I know that tangent is sine over cosine. So we're going to simplify. If we do that, we have get a common multiply top and bottom by cosine, as that is the inner denominator. You multiply the top by cosine, you have 1. When you multiply the bottom by cosine, you have cosine plus sine. Now if we were to plug in our pi over 2, you see it takes care of the problem. And you end up with 1. Cosine of pi over 2 is 0, sine of pi over 2 is 1. So actually, in this one, we avoided L'Hopital's rule, but that doesn't always work with infinity over infinity. This one did because we could do some manipulation with the sines and cosines. I will tell you, you've got to be careful about secants and tangent, because the derivative of secant is secant tangent, the derivative of tangent is secant squared. And when all things simplify, you still end up with a secant and a tangent, one on top, one on the bottom, and they just flip-flop. So you have to be careful about your secants and your tangents. Alright, here's another one, still infinity over infinity. Natural log of infinity is infinity, radical infinity is infinity. So we take the derivative. We apply L'Hopital's rule. The derivative of natural log is 1 over x. The derivative of 2 radical x would just be x to the negative 1/2. We simplify that. To simplify that, I would multiply both sides, top and bottom, by x to the 1/2. That's going to cancel out this one on the bottom, because that would give me x to the 0. And when you multiply the top by x to the 1/2, it leaves x to the 1/2 on this part right here. Now if I were to plug in my infinity, I have 1 over radical infinity, which is still infinity, which is 0. Another indeterminate form is infinity times 0. Again, it's a conflict of rules. Infinity times anything is infinity, but 0 times anything is 0, so it doesn't exist. Now, I rewrite these in a slightly different format. And that's the key on these problems here is whichever way you have it, whether it's infinity times 0 or it's one of the others, our goal is still to get to the 0 over 0 form or the infinity over infinity form, because then you have a top and a bottom, and you're able to take the derivative of the top, derivative of the bottom. You can do nothing with it like this. You can't take just the derivative of x and the derivative of sine 1 over x. It has to be in one of these two forms. Now, these are indeterminate, but these can be put in these forms. For instance, if I move infinity to the bottom, if I flip it to the bottom, if you flip infinity, you have 0. Or if you flip 0 to the bottom, when you flip 0, you get infinity. So you see it's a matter of form. So that being said, ladies and gentlemen, what are some ways we can get our functions into this 0 over 0, infinity over infinity form? Well, one way is just by simply flipping things. 1 over x is x to the negative 1. I can flip this x to the bottom and make it 1 over x, or I can rewrite that as x to the negative 1 power. Now if I plug in infinity, that gives me 0 here, and that would give me an indeterminate 0 on the top also. And see if I can get the slides to advance. There we go. So I apply L'Hopital's rule. The derivative of sine is cosine, but by the chain rule, we must also take the derivative of x to the negative 1. That's negative x to the negative second. And again, the derivative of x to the negative 1, same thing. Simplify. These can cancel, and I end up with this. Now I plug in my infinity, x to the negative 1, so that's 1 over infinity. 1 over infinity is 0, and cosine of 0 is 1. But the key was getting it into that 0 over 0 or infinity over infinity form. Our next form, infinity minus infinity, doesn't work. You can't do it. You can't take infinity away from infinity and get 0. So that being said, if we look at this, if I plug in 1, natural log of 1 is 0, 1 over 0, infinity. 1 minus 1 is 0, again, infinity. So how are we going to work with this? Again, our goal is we have to get this in a 0 over 0 or infinity over infinity form in order to apply L'Hopital's rule. So the first thing I do is I get a common denominator. I'm going to multiply this side right here, top and bottom, by x minus 1. So that becomes x minus 1 minus. I'm going to multiply this one top and bottom by natural log x. That'll give me a common denominator here. 1 times natural log x is natural log x. Now if I were to plug in my 1, I have 0, and I have 0 here, so 0 on top. Natural log of 1 is 0, and 0 on the bottom. So it is in the proper form now. That being said, I apply L'Hopital's rule. The derivative of x is 1. The derivative of 1 is nothing. The derivative of natural log x is 1 over x. On the bottom, I have to apply the product rule. The derivative of natural log x times x minus 1. That part's right here. And then we do natural log x times the derivative of x minus 1. That part is right here. If I were to plug in 1 now, would I still get 0 over 0? Do I need to simplify? Well, I'm going to simplify a little bit. If I take my 1 over x and I distribute it, 1 over x times x is 1, and times 1 is 1 over x, and then of course this 1 does nothing. Now we want to simplify a little bit further, so to simplify further, I'm going to multiply top and bottom by x. 1 times x is x, 1 over x times x is 1, and then that would become x, that would become 1, and that would become x natural log of x. Now, if we go back to the previous slide, what we end up with on the end is something that, again, is indeterminate form, 0 over 0. So I'll take the derivative again, and if you want to flip back and forth, you can. The derivative of the top just goes to 1. The derivative of the bottom goes to another chain rule. I mean, there's an x plus, and the derivative of x is 1. But then the plus part, that x natural log x, that's a product rule, and this is its derivative. So we simplify as best as we can. X times 1 over x is 1. 1 plus 1 is 2. Now what we end up with is something that is no longer indeterminate form. We can plug in our 1. The natural log of 1, I need to move my screen down, I see. Natural log of 1 is 0, and so that gives me an answer of 1/2. Again, ladies and gentlemen, I apologize for this video. My computer is doing funny things, but we are near the end of the 15-minute mark, so I'm going to pause here, and we'll restart the next video momentarily.